Okay, let's go to system of conservation laws. Finite volume and actually also finite difference are not very difficult with not just one conservation law, but a system of conservation laws. A system of conservation law is going to be multiple quantities coupled with each other. In a conservation law sense, that means the flux of one quantity is determined not just as a function of that quantity itself, but as a multivariate function of several quantities. The simplest type of conservation law is coupling two quantities. So the time derivative of, let me illustrate it in a scalar sense, the time derivative of u1 plus a flux, I call it 1, of u1 and u2 dx is equal to 0. Also, the time derivative of u2 is a function also of u1 and u2. If f1 and f2 are both linear, then this is not very different from the second project we just submitted last week, right? But in this case, f1 and f2 can be nonlinear functions. So I'm just going to give one example that is exactly like that. It's called the shallow water equation. Shallow water equation is an equation that models the movement of water, of any fluid, under the influence of gravity, a shallow layer of water. It actually describes, for example, the waves on a beach pretty well before it breaks. So, and you can do a lot of interesting experiments with it. And the reason actually, if you look at the movement of waves over a beach, and the reason the wave breaks is in this shallow water equation is going to appear as a shock wave in the shallow water equation. You're going to create a discontinuity in the height of the water, which in real case it'll just fall down and break as a wave. So in the shallow water equation, the two quantities we are modeling are, first of all, the height of the water. So you have, let's say, a water column like that. So the height of the water and also the velocity of the water, right? How fast the water is moving either towards the left or towards the right. And in reality, the reason that h is a conservative quantity is because we are modeling water as incompressible. So h integrated over x is what? So if you integrate h over x, it's the volume, is how much water you have. And velocity doesn't really integrate to be a conservative quantity. So instead, we use u times h as a conservative variable. If you multiply u over h and integrate over dx, what do you get? Also, we need to assume the density is a constant, which is the case. So if you multiply rho times u times h over dx, what do you get? The momentum, exactly. So these are the two conservative quantities in this equation. And we can see how the flux of each quantity is going to be a function of the other quantity. For example, in order to derive this equation, it's actually a lot easier to derive it from the integral form. So d dt, for example, of the integral over a and b of h times dx, which is the total amount of volume, or total amount of water in between a and b, is equal to the flux into the volume minus the flux out of the volume, right? What is the flux of water into the volume? Yes? It's actually H, yes, multiplied by U at point A minus H times U at point B. So it's going to be A and B, right? Okay, so that means the time derivative of H, I mean here H times U is the flux. The flux depends on not just H, but also some other quantities. Now, how about this other quantity? How about the time derivative of rho UH times dx? How does the momentum change in time? What is the momentum flux? It's a little bit more complex, right?
Rho HU squared.
So first, there is a term UHU squared. That's basically the momentum itself times U. That's how much momentum is going. That's the momentum carried by the fluid going into the volume, right? So that's one term. Interestingly, there is another term that wouldn't be here if there is no gravity. The gravity is going to create a pressure force that acts on surface A and surface B. And the pressure force is going to create a momentum. It's going to create a system in the momentum, but because the pressure only applies on the two interfaces, it can be written as a flux. And that flux is going to be the average height of the column. So if you take the center, that's the average height, times rho g. Right, so that's the momentum flux, and that's the force. Again, at A and B. So with these two integral forms, we can derive the standard form of the conservation law. So, sorry, dh dt plus partial x of hu is equal to 0, and partial rho uh partial t plus partial x of rho hu square plus half of rho gh is equal to 0.
What is the two factor? The average height is given by.
Oh yeah, this is because if you integrate the pressure force over the column of water, the pressure is equal to 0 at the top, right? So there is no pressure at the top. The pressure at the bottom is rho gh. Oh, actually there is because there is an integral, we have a square. Yeah, sorry, we have a square here, right? So we are integrating the pressure at the bottom is rho gh, and we are integrating over a height of h. So the total pressure force is half of rho gh square. All right. So now if you say this is not in standard conservation form because there is a weird rho hu here, right? That can be fixed by just a change of variable. So let's say we define this momentum equal to rho uh. Then let's rewrite these two equations as the following. So the hu is going to be partial x of m divided by rho, right? Rho is a constant. And partial m partial t plus, we also write the flux as just a function of m and h. So in this case, we have a u square, which means we have to square this m By squaring m, we have rho square, u square, h square. So to get this rho hu, we need to divide by rho and divide by h. The second term can be just written as half of rho g times h square is equal to 0. Now both equations are written in terms of either constants like rho and g, and these two conservative quantities h and m.